Now we get to the fun part, which is actually taking derivatives. So we'll start off by calculating delta. So the delta of a European call option is the rate of change of C of ST. So again, remember, this is the actual Black-Scholes pricing formula. So even though I've written it here as C of S comma T, it's really a function of all of the 7 variables that I had on the first set of slides. And I'm going to take so it's the rate of change with respect to the asset price S. So how much does the value of the call option change as the price of the underlying asset changes? And so mathematically, I can write that just as delta is equal to the partial derivative with respect to S of the Black-Scholes pricing formula for a European call option. And so this is the pricing formula for a European call option that I had in the first set of slides. And I'm just going to go ahead and start using the rules we've been developing earlier in this course to start taking the derivative here. So the first thing I'll notice is that the pricing formula has 2 terms. So I can use the linearity property of the derivative to write this as so this is a sum, essentially. And so the derivative of a sum is the sum of the derivatives. And then I'm also, in this one step, going to combine the scaling property. So when I'm taking the derivative with respect to S, so I'm taking a partial derivative with respect to S, anything that isn't a function of S I can treat as a constant, and any constant I can move across the derivative operator. So in the first case here, this part, the e to the minus qt minus t, that doesn't depend on S, so I'm going to take that out, and I end up with e to the minus qt minus t times the partial derivative with respect to S of the product S times capital phi of d plus. And on the right-hand side, I'm going to do the same thing, except here I have 2 parts that don't depend on S, so I can take those across the derivative operator. So I have minus k e to the minus k e to the minus rt minus t times the partial derivative with respect to S of phi of d minus. And so the next step here is both phi of d plus depends on all of the arguments of the Black-Scholes pricing formula, including S, and so does d minus. So this is, I'm going to look at and say that's the product of 2 functions of S. That's S, which is a very simple function of S, and phi of capital D plus. So I'll have to use the product rule on the first term. And so the product rule says if I have the product of 2 functions, I take the derivative of the first function times the second function. So that gives me just a capital phi of D plus the first function S, so this S comes from right here, times the derivative of the second function, so times the derivative with respect to S of capital phi of D plus. So now I have a pretty complicated formula. So what I'm going to do is kind of attack pieces of it, and then we'll be able to put all of those together to get an expression for delta in the end. So the first thing I'm going to look at are we have these partial derivatives with respect to S of phi of, and so I've used this plus minus sign here just because these functions are very similar. So quite often when I take derivatives of that, I'm going to get the same answer. If not, I'll put a plus minus in where it's important. And then if I'm just talking about d plus, you think of this as a plus. If I'm talking about d minus, you think about this as a minus. So the chain rule says that if I want to take the derivative of capital phi of d plus with respect to S, that's going to be equal to the derivative with respect to its argument, so with respect to this d plus or minus, of phi of d plus or minus, times the partial derivative of d with respect to S. And now remember the definition of capital phi was just we were integrating from minus infinity up to d of this function lowercase phi of x dx. And so I like to use the shorthand notation, little phi of x, for this function here. Just it saves me writing some stuff. Also, it's less likely that I'm going to make a mistake if I just have to write that down rather than this whole expression. And we saw in the second week how I could take the derivative of something like that. So it's just the derivative of an indefinite integral. And so again, I'm doing the same calculation 2 times. So it's either I'm treating it as phi of x or I'm treating it as the actual expression for that function. And then when I evaluate these, it turns out that the derivative is just lowercase phi of either d plus or d minus. And then that has this functional form on the right-hand side here. So that gets me this part, the derivative, the partial derivative of capital phi with respect to s. So what I have so far, I have this expression for delta. And then we just evaluated this thing here and this thing here. So I have this expression for the derivative of capital phi. And I still need this part here, so the derivative of the partial derivative of d plus or minus with respect to s. So I have the first term here is this guy. And now to get the full derivative, I still need to evaluate the derivative of d plus that kind of came out by the chain rule. So I'll move one step ahead with our formula. So I'm going to substitute this result here, this result in the second line, into the first line to update my expression for delta. But I still have this partial of d plus with respect to s and partial of d minus with respect to s. So that's what I'm going to do in the next slide. So I need to compute the partial derivatives of d plus and d minus. So remember from the first set of slides, I said I gave definitions for what d plus and minus looked like. And so now I can write them as just one formula using this plus minus notation. So the only difference between d plus and d minus was this plus or minus sign here. So I've just replaced it with this little placeholder. And now I want to take the derivative of this with respect to s. And so I'm going to make a little simplification here. So if I have a sum in the numerator, I can write this as log of s over k divided by sigma times the square root of t minus t. So that'll be one fraction. And then plus r minus q plus or minus sigma squared over 2 times t minus t divided by sigma square root of t minus t. So that's a second fraction. I'm just adding those two fractions together. And so the reason I'm going to want to do that is because after this s here only appears in the first one of those fractions. So what I'm going to end up with is I'll want to take the partial derivative of the leftover part with respect to s, but there's no s's in this part, so I can treat that as a constant. So this term on the right-hand side, that's just going to go away. That'll be equal to 0. And then I'm left with 1 over sigma times the square root of t minus t times the partial derivative with respect to s of the log of s over k. So I'll do a little substitution here. So I'll let u equal s over k. Then I can rewrite this here as the partial derivative of, with respect to s, of log of u. And so by the chain rule, that's going to be the derivative of the log times the derivative of u with respect to s. So the derivative of log of u is just 1 over u. And then I have this partial u partial s. And I'm going to calculate that just by taking the partial derivative with respect to s of u here. So that's going to be 1 over k. So what I'm left with is 1 over sigma square root of t minus t, k over s, So u was s over k. If I take 1 over that, I get k over s. And then times 1 over k, which is just this partial derivative, partial u, partial s, which popped out because of the chain rule. So we'll see that the k's are going to cancel here. And I end up with the partial derivative with respect to s of either d plus or d minus is just 1 over s times sigma times the square root of t minus t. So in this case, I was able to get both of those calculations because the plus or minus bit didn't depend on s, so that ended up being 0. So it wouldn't matter if I was taking the derivative of d plus or d minus. I'm going to get the same expression here. So putting everything together, all I need to do now is I have this is my most up-to-date expression for delta, but it still has this partial derivative of d plus and d minus with respect to s. But that's exactly what we calculated on the previous slide here, so I just have to put a 1 over s sigma square root of t minus t into here. Oh, whoops, I guess I had it on the next line. And so that's going to give the following expression for delta. So I'm going to get e to the minus q t minus t times capital phi of d plus. And then I have the rest of this in light gray. Because if you look in the textbook, this is the entire... Oops, maybe I get it backwards. Nope. Just the part in the dark black is the entire expression for delta, but we still have these other terms left over. And so in the next set of slides, I'm going to go through an argument about why that's going to be equal to 0.